Welcome everybody, and hello, glad to be here and talk about the effective heat removal from a packaged data center based on a two-phase immersion cooling. There is a case study what I wanted to report about, and this presentation was more about the immersion topic in that mobile data center, wanted to let you know what we did and call for actions to do more. So the case study I wanted to introduce you about for the next 10-15 minutes. The challenges what we had with integration were quite big, and then the two-phase heat transfer from chip to dry cooler. It's the most important parts to get the heat away, and I wanted to let you know how we did that. Then we did that with a roof-mounted cooling container, a special engineered thing. Then how we control it and what we should do next. So here it is, the case study. What we were building was a 40-foot container full of data hall. We call it the data hall, the lower one, and the upper one is meant to be the mechanical plant room. Yeah, so it is a 40-foot container, standard size, ISO containers. It is transportable. It is pre-manufactured. We do that in our Singapore factory and make that ready. It's the rapid deployment prepared. Two-phase tank are in, and then we were deciding for high performance computing. It should be HPC ready, so we decided for a megawatt. And the cooling generation always is important, so the indirect free cooling with no chillers was the decision here. We made it company internal. We wanted to have a proof of concept and measure the values. First, the safe operation of this was a focus that people can work with it and then have a low POE and be sustainable. So the requirements are cost-effective, rapid, HPC ready, and sustainable. And then it's clear it is a two-phase immersion. The mobile deployment here, short introduction. In the lower one are the tanks and electrical distribution control, and in the upper is then the mechanical thing. And we have two containers which are, let's say, put on top of each other. Once the lower one is in place, you put the upper one on top, have a little connection piece of a tube. You devent it and connect it hydraulically, electrically. Cables are pluggable, so very rapid. That's the principle for this mobile deployment, that you are fast. That's let's say standard requirements. But now coming to the cooling part, this is the very important one, and how the tanks are cooled. So we have two 60U tanks. Both are there with 3 meters by 2 meters by 1 meter, quite big machines. Space management was the challenge. How to organize that operations work. So you see here on the top, we had to integrate a mobile crane system. You can move the cranes over the tanks to the car, to this little cart parked on the side to get the servers in and out. That's the challenges for operations, and the safety measures in closed containers were important to maintain, because of people must be safe in such a mini space of an ISO container. And then during the design, our safety guy came in and said, all right, here is the rules and the regulation for escape ways. So we had the long list of things to integrate and said, okay, we squeezed it into a container, but then the space was only half the space because of he wanted a meter of escape roads, and we rearranged and had used it to the maximum here. But for this forum, I wanted to concentrate on the heat transfer. So it is in 3 steps. Yeah? First, the evaporation process, then we condensate, and then we bring the heat to the free cooling on the roof mounted. So our measure was 8.5 kilowatt per U. What we wanted to bring away. So this is 500 kilowatts for a 60 U tank, and we have 2 of those in our container. There is an intensive heat flux, and through the evaporation, the actual advantage for that cooling method. And we are not on the limit. The fluid can do more. Yeah. Always decides the cooling generation, how much cooling you can provide on a given space that, let's say, defines the IT capacity. So we decided for that megawatt and bring all the hardware in the tank, and you see it here, boiling here. It's a Chemours pictures. We work with them for a 49 degree boiling point. From the environmental aspect, there are, let's say, fluids which have low GWP and ODP and high operational safety. So we decided for the Chemours fluid, the 2P50, and the other one, the Unistar Chemicals Unisolve IC, and test both and see how the performance is. We wanted to see how much reserve is in the fluid and how it works thermodynamically. And for our test, we do not have computers to test here. We use adjustable heaters, and then we switch them on and off and simulate the load, and are expecting a very low POE of 1.05. So this comes together of about, we have 2 end pumps. One is running, it's about 8 kilowatt. Then we have 18 blowers there on the top. Altogether should do about 40 kilowatts, so 50 kilowatt parasitics over 1 megawatt of IT would be 5%. So that's the goal. So in the second step, after evaporation, there is a condensation process. We work together with company Wieland there. Wieland is a tank maker and a development partner to do the condensation after evaporation. And same thing like in the fluid, there is reserve in the condensation density. The special tube, what you see here, is optimized for the heat transfer coefficient. It's amazing what these tubes can perform. And same thing, we could pack more IT in such a tank if the cooling would let us. Yeah? Same thing, we go here with a cooling temperature in 33 and out 43, and we'll operate it. And the challenge is the same thing. The changes of the load, the fluctualization of AI is not a flat load. What we maybe see with Bitcoin mining, this will go up and down, and the control loop will then give us the certainty that tank operates fine. Even in Germany, when we bring it then over here, we have a winter case, minus 14 degrees. We don't want to start up a tank with minus 14. We have measures for the winter case. So step number 3 is the dedicated roof-mounted cooling. As I said, we optimized the cooling space. The 2 blue ones, what you see here, they are the coils, the heat exchangers to the air. On the top of the roof, we have 18 actual fans. That's the most sustainable way to move air with actual fans. And we use all the space. They're 12 meter long, 3 meter high, and both sides. That's the maximum what you could do. And the deepness of the heat exchanger can vary. So we adjusted it for a warm environment for a megawatt. And brought the respective hydraulics in it. Same thing on the lower data hall container, the upper one. If somebody is doing maintenance, you have to have a possibility to escape. So we did stairs, and at the end had only half the space to integrate it all. This was not so easy. The container is meant to be pre-flushed, pre-filled before shipment. There is a buffer for expansion of fluid if during transport it gets hot, or warmer, or colder. So that's taken care as well. We cover it up with sheet metals on top and on the side to protect the equipment. So these 3 steps, evaporation, condensation, and free air cooling, is the main thing of the container. And here is how we want to control this. The system process and instrumentation diagram you see here with the actual fan groups on the top of the container. Then we have on the left side the ambient air exposed coolers. We go through 2 tanks, have then 2 pumps, and this little pass around here around the coolers is our winter case management thing. And the 33 in and the 43 out will be the important things to control that tank operation goes fine. For persons, we have a fresh air system, which is not on that diagram, because if somebody closes the door on this data hall, you needed to be sure that persons can be okay and have enough air to breathe and cooling. A lot of alarms are there for oxygen, air quality, smoke, leaks, and CO2. It's all integrated to be safe. And the fan speed adjustment to have the respective air mass against the cooling, what is needed for the tanks. That's the critical part for these control loops. So that's the case. What needs to be done, and I'd like to call for action here, that the safety requirements, the serviceability, we talked yesterday in the cooling bazaar about how easy it is to service. That needs to be worked on. Then the material compatibility, we had just a presentation that hardware is okay in the fluids, is solvable, and see what kind of boundary conditions we have. It is all discussed in this wonderful community here of Immersion, a lot of groups, and please contribute that things have a chance and get your experience in. So thank you, and I'm ready to take a question in case.
Hi, Manfred. It's Konrad Kaminsky with Standard Fluids. Manfred?
Oh, here. The light is crazy. Hello.
My question for you is, in the tanks in the container, how much freeboard are you keeping above the condenser coils?
The space above the fluid is there for hardware to be immersed. It's about 900 millimeter free space downwards, and then there's a fluid level, and then there is a condensate pack, one on the left side and one on the right side of the long side. To answer a question, it's about 40 centimeters, and we use a lot of copper for to be sure the condensation process happens well, and we'd like to test out how many reserve is it to be condensing more. But as I said, the condensation rating, the capacity is made by the cooler upstairs.
Thank you.
Sure. All right. So, danke schön.